Hi, and welcome to this new chapter, in which I would like to start our journey with an application on a certain language that you know already. So I think you're more familiar with Java than anything else. So why not to start with multi-threading and particularly in Java? The outline will go as follows. In this first part, we will give a quick motivation. I will show you what's the difference between processes and the threads, and then I will show you how to create threads with Java and how to call them and what's the effect of that with a live demo inside NetBeans. Later on this week, we will check the detailed API and particular use cases. And after you start working on some exercises, next week we'll discuss the synchronization. So why do we use multi-threading? As we said in the introduction, um, we may want to achieve two or more different tasks in parallel or almost at the same time, such as doing the same task but really in parallel to accelerate the final outcome, or simply doing different subtasks. Okay, so to do it in parallel just because it's required as when you were driving a car. Good. So in practice, if you want to read a long file or copy a long list of files of high sizes, and you want to display a progress bar gradually, then you need to do it in parallel actually, because otherwise the interface would be freezing. Whenever you have a long operation actually, and you want to avoid freezing your graphical user interface or GUI, then you need actually to use multi-threading so that the long operation is handled to a different thread, and then your main thread keeps doing the main action, displaying the GUI, refreshing it, and so on and so forth. And then when the thread finishes, it would display or update the GUI by displaying the results. You may want to achieve tough computations quicker using your multi-threading capability on your processor, or you want to serve several different requests in parallel, as you used to do in websites or chat programs. Good. So why don't we use multiprocessing actually? Maybe you're already familiar with what you learned in operating system. You can use the fork uh, instruction to create multiple processes, and then the system will juggle between them and switch from one process to the other. Um, and this happens actually all the time. Your operating system switches between one process and the other, even if fork is not called. Um, for example, when you receive a Skype notification while you are sending an email and listening to music, then here you have multiple programs running in separate processes, um, and the system is providing the almost near real time switching between those processes, although everything goes in sequentially in one single core. And by core, we mean a single unit of computation where you have an arithmetic and logic unit, and you have all the needed buses to go to read from the RAM and to write to it, and so on and so forth. So you have a full von Neumann model for computation. Um, so in this case, everything will go sequentially. We all know it, but simply since we have processors of few gigahertz, then it means they can accomplish billions of instructions per second. And this is why if we do hundred of millions of the first one, hundred of millions of the second process, and we switch very quickly between each one of them, we will have this impression that the execution is really happening in parallel. When it comes to one single process, such as Skype, if you were running two different services, such as the payment service and the service responsible for showing the available persons, then the Skype process may use fork for creating multiple sub-processes and benefit from the first class scheduler of the operating system. In fact, it's as if Skype is willing to get more CPU attention or more CPU time. You know, if you have kind of a round robin scheduling, then the Skype process would appear in this case, twice Skype number one for the process checking who is available online to update you, and the Skype number two for checking who is gonna actually who is going to send you a message, for example. So it shows you notifications for newly received messages. And in this case, it could be that Skype number two is a child process of Skype number one. Okay, so regardless whether they belong to the same process or they are separate, you already know that the operating systems have this ability to juggle between processes, and to hence they can be used. This mechanism can be used to achieve kind of a parallelization. However, multi-threading is about programmatically achieving or executing concurrent code inside the same process or the same program. So let's see how it happens. So within the same process, so this is only one single process, you'd see the threads somehow running in parallel, and it's up to actually the Java virtual machine, the JVM engine, to juggle between those threads and to allocate a certain amount of time for the first one, to go to the second one, and then to the third one in a, for example, round robin like scheduling. Although you will see that we can actually associate to each thread a certain bigger amount of time with respect to the other by increasing its priority while defining the or creating the thread. So we'll see those details later on. But at least now you know that all those threads, they belong to one single process, and then that it's the Java virtual machine that will juggle between them. But for the operating system, they will be seen as one single process. So let's see this pictorial element that would show you how the difference in handling threads and processes by the operating system is taking place. So actually, if you have a certain task that you want to execute with three different processes, then using the traditional multiprocessing model, you would create one process each time you want to achieve one additional task. And within each process, you didn't know, but in each process we have at least one thread that we call the main thread. Okay, hence the name of the main function. So it's one main thread that is being executed within each process. But then it's up to the operating system, which is kernel, to switch between these processes and to ensure their parallel execution, whether they consist of the same task, the same sequence of lines of code, or different lines of code. But the same model or the same functionality actually can be achieved with a different model, with a multi-threading model, where actually one process has three internal threads. And then when the process is granted a certain amount of time, it alters the execution between the multiple threads. Thread number one and thread number 2 and thread number 3. Okay, so instead of using 3 processes, here we are using only one single process and the 3 threads inside it. So in terms of structure, what do we have in terms of structure between single-threaded processes and multi-threaded processes? Well, you maybe already know that what's shipped inside the memory space of a certain process is the block of code, the lines of code, the data block that actually holds the dynamic values of the variables that you allocate within your code and manipulate within your code. You may also keep a track of the handles of few files with which you are doing certain input-output instructions. They could be hard disk files or network files, whatever you want. You have a stack for the execution, a stack that or a heap that increases in size or decreases, and you have a bunch of registers that correspond to the live execution, because when you want to context switch between this process and another one, then you have to save all the registers of the current execution in the processors to free the processor and to allow for another process to come in and then to unfold or restore its registers inside the processor to start executing. One of those registers is the PC, the program counter, that actually pinpoints towards a specific line of code. So for example, if PC is equal to 52, then it means that this program or process has reached the line 52 of the assembly code to be executed. And this is why when you save this process and you switch to another one, if you come back later on, you will resume the execution exactly for the same line of code and with the same context of data. So I won't dig deeper on this because you already learned those concepts of context and context switching in the operating system course. Okay, good. Once again, in a singly threaded process, we have only one thread, and the execution of the code goes sequentially. The operating system may juggle between this process and another one, but inside the process, everything goes sequentially. Nevertheless, in a multi-threaded model, well, we can have one single segment for the code, one single segment for the shared data. Think about it in terms of Java code as being as the static variables that you globally make available for all your classes, all your threads, all your functions, including the main function, the shared files, and so on and so forth. But internally, you can hold multiple registers for each thread, and you can have also a different dynamic heap for each one of the threads. So you can have stack number 1, stack number 2, and stack number 3 for each thread. You can have program counter number 1, program counter number 2, and program counter number 3. So nothing prevents you from having program counter number 1 being 3 to indicate that thread number 1 is still executing at the line number 3 of the code here. But to make program counter number 2 for thread number 2 be equal to 55 and program counter number 3 equal to 0. Let's say thread number 3 did not even start executing till now. Okay, and inside the stacks, you can have different variables. So you can have x being equal to 2 here and another local variable having the same name being accessed by those lines of code, but having a different value that is equal to 5, and so on and so forth. I think this is not completely new for you because you still remember the fork instruction that returns a certain process ID. Actually, if you defined a certain X before the fork, and you made it equal to 0, then it's equal to 0 in all the processes. But once you start making within an if PID is equal to 0, then um, x make x 10, else make x become 12. Then I think from this moment on, everything you do depending on the process ID uh, would actually be executed separately according to the underlying process ID. So usually the process ID is not equal to 0 in the father process, in the main process that forked a child process from itself. So this means that this code is executed within the child process, and this one is executed in the main process. Okay, well, regardless whether this is totally correct or not, um, anyway, you know that it's one part that is executed in the child and another one is executed in the main, and you have this trick here to distinguish between the main process and the child processes. And you know, you can have different program counters in this case. Here you may have different lines of code, and there you may have different lines of code too. So this is exactly what you can achieve with multi-threading, but using certain API from your programming language. Let's dig a bit deeper on the technicality before starting with the practical part. So what are the characteristics of threads? Well, actually, threads have execution context or state included in the registers plus the stack, as we just saw. The thread context is saved when not running, okay? So that we can get back to it later on. It has an execution stack and some pre-thread static storage for local variables. And it has access to the memory address space of the whole resource and to the resources of its task or process. Okay, so all the threads of a certain task or process share those memory and resources spaces. And when we are actually talking about this part here, okay, so they are shared among all the threads of one single process, and which allows for synchronization, kind of, in this case. And when one thread alters, what I mean by this, actually, if you have a certain common memory space, so imagine that you have a very large array denoting a certain image, a large image that you want to process really in parallel because you want to accelerate this process, given that you have a multi-threaded processor. So the first thread can go and read the first chunk of the image. The second thread can read the second chunk. They can work on it and then write back the results. Okay, and so that finally one thread of them continue by displaying the image on the screen or saving it to the hard drive or sending it over the network. Okay, so this sharing ability is really fantastic, because otherwise between processes you cannot do this. You need to use inter-process communication, or shortly IPC, and check how to do this with Windows, for example, using C code, and you will see that it's not that easy. And the idea behind this is to protect actually the various memory spaces of different processes, and to avoid that one process gets into the memory space of another process. So they have to use a very strict protocol that goes through the kernel of the operating system to make sure that they are able to exchange data. Okay, and they have to agree on this. The first process has to expose this data, and the second process has to read it. Good. Well, you don't have those restrictions with the threads. Okay, once again, all the threads belong to the same process, to the same program. It means that they have been developed by the same developer or by the same team of developers. And why not to share the same code and the same program content? Okay, there is no reason not to do it. When one thread alters a non-private memory item, it means a shared item, all the other threads of the same process or task see that. And this is really fantastic, as I said here in this illustration. A file open with one thread is available to the others, and hence you don't need to open multiple file handles and to occupy a larger memory space in this case. Okay, so I think this is really nice. How can we use a thread? So consider an application that consists of several independent parts that do not need to run in sequence or that actually need to run in parallel. So each part can be implemented as a thread in this case. Whenever one thread is blocked, waiting for an input-output, or just because you need it, so the execution could possibly switch to another thread. Okay, so not only when it's waiting, but also when needed, because you want to make a certain progress on two different tasks really in parallel, showing a progress bar and loading a file at the same time. So instead of blocking the whole application, the other thread can work can use the CPU time to do something else. Since the threads within the same process share memory and files, they can communicate with each other, as we saw in this illustration here. And they do not need to invoke the kernel in this case, and there is no permission or security issues. Therefore, it's necessary to synchronize the activities of various threads so that they do not obtain inconsistent views. Okay, so once again, if I go back to my illustrated example, I draw this line here, neat line, to show you that there is a phase where the first process is writing to the array, the second process is writing to the array, but they need to synchronize with each other to make sure that both the threads have finished before uh, giving the output. Okay, so you have a read phase that can be done in parallel. There is a computation phase or processing phase that can be done in parallel, but then the output should only be displayed when the final result is consistent and ready to be displayed. Okay, what's the benefit of using threads? Well, they allow parallel activities inside a single address space. While one thread is blocked and waiting, a single thread in the same stack can run, and they need less time to create and to terminate, actually with respect to processes. Okay, because we don't need to another address space, the memory allocation, paging, and so on and so forth, and scheduler item. So it takes less time to switch between two threads than between two different processes. You know, the scheduler need to know all the process um, 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 identity blocks, okay, the PIBs, process number one, process number two, and to keep them in a certain queue. So you have multiple queues. If you still remember from the operating system course, you have a waiting queue, an execution queue, ready queue, and so on and so forth. So adding more processes, if Skype wanted, if I go back to this example here, if Skype wanted to implement two different tasks using the process model like this one, okay, then it means more and more handles in those queues. Each time a context switching would happen between these two different processes, sub-processes that belong to the same program to Skype in my example here. So but with multi-threading, it's much easier to switch, and most probably this would happen at the application level, at using the language primitives and not the kernel primitives. So it happens without disturbing the operating system um, precious time. Um, so without disturbing the operating system scheduler and consuming its precious time. Um, we can also have inter-thread communication and synchronization in a very fast way in comparison with processes. Because of their nature, threads can take advantage of multiprocessors when you have multiple cores, let's say quad cores, with logic and arithmetic unit in each one of the cores. Then usually each thread can go to the to a different core if the programming language allows for it, and while having the same memory space in the RAM. Great. So chip. Usually you will have different buses, but you can have this shared memory space inside the RAM. So let's recap a little bit while comparing to processes. So processes, they have separate address space. Threads, they have shared address spaces. Processes, they need explicit inter-process communication, IPC, but threads, on the other hand, they have separate program counters and the stacks, and the communication between them is done through shared memory. So they don't need inter-process communication. The synchronization part of the communication is the synchronization in case of processes is part of the communication between them. So when one process is producing a certain result for another one, it should wait until that process consumes this value or result, and vice versa. The first process should wait until the second one finishes before it consumes this value or displays it. So it goes, the synchronization happens because we should explicitly handle communication between the processes. But here, actually, the communication is implicit, so this is why we need to explicitly synchronize those threads using multiple routines. So just to give you an idea, as you used to use wait in multiprocessing, sorry, yeah. So we have wait here, usually with pthreads and with Java threads. So pthread is in C++, and we have the class of thread that we will learn in a few minutes in Java. It has a certain join method that we are going to learn more about it on Friday. Good. More about the details and the comparison between threads and processes. So similarly to processes, threads share CPU and only one thread is active at a time, because once again, if we have one single core, then everything goes sequentially within that core, and we have to context switch between the thread. Although if you have, let's say, quad core, so maybe you can use all of them, each one of them for a certain thread. But what if you have 16 different threads that you want to execute in parallel? Well, once again, you will need to switch between 4 times between each thread and the other, okay, to have them execute in parallel, okay? So within a process, they execute sequentially. They can create children. So a thread can create another thread. And if one thread is blocked, another thread can run, okay, as for the processes. Unlike processes, they are not independent of one another. For example, if one of the threads would crash with an exception, well, the whole program, including the main program, would actually halt with that exception. The second point actually is that all threads can access every address in the task, okay? It's unlike processes. Well, we already talked about this when we talked about the communication part, and threads are designed to assist one another. using also this communication mechanism. Note that processes might or might not assist one another because they may originate from different users. And in this case, maybe they won't have the right to do it. Okay, now let's come to some practical stuff. How to achieve multi-threading in Java. Well, this is quite easy. You will see. Let's imagine you want to do a certain job in parallel. Well, just make this job extends a thread. So this is how you define a thread. And in the thread class, you have a run function, public void run. So you can override that function. You may call super.run, although it does not do plenty of things. And then you do the job to do here. You write your code here. Good. So this is how you define the thread, not how you call it. Let's see how you call it. So I have the same definition here once again, but how to call it. So using another class, let's say, or maybe within the same class, you can create a main function. You can instantiate your class. So here I'm creating an instance of the job in parallel class. And I'm calling what? Haha, I overrided the run function, but I'm actually calling the job.start function, although I'm not redefining this function. So to use a thread, once again, I instantiate my thread class and I call job.start. And then I can actually do whatever other things I want to do in my main function. So please remember that you do the following. You write your code in run, but you should call start, which causes the Java virtual machine to do a lot of stuff behind the scenes with its scheduler in order to eventually call run in parallel with the main thread and with all the other threads, and to start switching between the context of execution that it has within run. So all your code goes here in run. The program counter of your thread would point towards lines here. Of course, if your task is maybe checking every 5 seconds something on the internet, so maybe you have a loop here, okay? And this is why this thread is candidate to be stuck, okay? You cannot do this by calling run here, okay? So if you call run directly within the main, this is completely wrong. If you say job.run, then you are making a traditional function call as you used to know it in Java, and this is blocking. Okay, you cannot go to the next line until this call finishes. So if once again, if this code here is checking a certain server, whether the server becomes available or not, then this might be an infinite loop until the server responds. And maybe you want to do some nice stuff here. You don't want, while waiting for the server, you can do something else, okay? And you want to wait for the server in the background. So this is why job.run is blocking, and to avoid it, you should call job.start. Otherwise, you won't have real parallelism, okay? We will see it in a few seconds with the live demo. So, but just it's worth noting that you can either extend the class thread as shown in this slide, or actually you can implement a certain interface called Runnable. While with Runnable, you make your class implements Runnable, okay? And you override the run function, but then when you create your class, you need to pass your instance to the class thread. So you create in the main a new thread, a new instance of the class thread, not your class only, and you pass your class instance to it as a parameter. So yeah, no, I want you to think about the constructor signature. What could be the parameter of this thread? So I have three questions here. First, that I want you to prepare until next live meeting. What is a method signature? Okay. The second question is, what could be the method signature of the thread constructor that we have here? Okay. And the third, which is maybe the most important, why may we need to use Runnable, okay, to implement Runnable and not to extend thread. So please think about those questions. We will discuss them next time, along with the more advanced details of the thread API in Java. Okay, so this is our next duty, but I will end up the theoretical part with this with these questions.